Thanks for coming to my COSIC seminar on the paper titled MixMatch Flow Matching for Mixnet Traffic. This is work by me together with Marc, Enrique, and Claudia. And it's appearing in the Proceedings of Privacy Enhancing Technologies of this year. So the conference is going to be in a couple of weeks, and I have to go present it. So to set the stage and motivate this research a little bit, okay, so let's say set the stage with communicating privately online, which is something that I think we would like to do and we all work on in different capacities. For example, by now we have pretty good payload protection, right? Whenever we want to send something to only a specific circle of people, we have strong schemes by now that protect the content so that only these people can see it. For example, advanced end-to-end encryption schemes and standards and protocols, right? However, there's a second access to this, a second place where we have to think about the privacy that we have when communicating online. And this is on the network level, right? So this is the whole metadata problem, because an observer that is just looking at the pipes that connect these systems together can, of course, see the metadata of the packets that go across them, right? So this metadata includes the source network location, but of course also the destination network location, which, for example, when you're looking at the port, and the port is relatively predictive of what kind of application it is that is using this or is sending this packet. You have, of course, data such as the timestamp. It's a very important one, and of course also the size, right, of the packet. So this is just metadata that occurs or is generated when you send packets, and you cannot do much about it. In fact, it actually is necessary to route your packet, right? And this is just for one packet, but of course you can do this over time. So you go from just observing the metadata of one packet to observing the metadata of many packets, so many observations, and then patterns start to emerge, right? So you can think about, okay, the frequency and the interleavings of this exchange of these packets online. Okay, great, this is blocked. So ideally, okay, maybe this is enough. No, okay, you have to live with this, sorry. Ideally, we would like to have strong protections on the payload level as well as on the network level, right? So payload level protect the content, but then network level do something against this metadata collection that might allow an adversary analyzing this data to make inferences about our behavior, our actions online. And a very well-known, very well-established, and by now relatively old concept already is the concept of mixnets. It was introduced in 1981 by David Chaum, and to just give you a rough impression of what a mixnet works like at a high level, let's look at this figure. So you can see here 6 endpoints communicating via the mixnet in the middle. The mixnet is represented as only 3 mixes, M1, 2, and 3 here in this case. And in this configuration, they're set up to be working as a cascade. That means all the packets go into mix 1, go through the mixnet, right, the chain of mixes, and then leave from the last mix. You can see here endpoints 1 to 3 sending each one packet to the other side at different times, right? The packets enter the network at different times, but as you already can see, they leave at the same time, right? This is kind of the goal. You want to obscure which packet is which going into the mixnet and coming out of it. So there's the question of timing. When does a packet enter? When does it leave? And of course, like representation, like can you track it just on how it looks on the network level? So the mixnet design space is relatively vast. So you can realize a mixnet in very, very many different ways. But as an example, in this case, the mixes perform 4 basic operations, right? Whenever they receive a packet, they will decrypt the layer out like around the packet that is related to their cryptographic key material that only they hold, right? So that already changes the network representation going into the mix and coming out of the mix. They will assemble a certain number of packets, and again, this is really up to the design of the mixnet how this is done. They can batch them, for example, together, but then crucially, they will reorder them, right? So it is not clear that the packet that went first into the mix comes out first, right? There's no relationship in this sense. And then they forward them either to the next hop or ultimately to the final recipient, right? And this way, even if an adversary, so the adversary here in red, is able to pretty much control all links and all nodes except one mix, the guarantee holds that there is no clear relation between the packets going in and coming out, like which one is which, right? Because even if there's only one honest mix left, it will perform this action of like gathering together and destroying their time and look correspondence going into the mix and coming out. Okay, so in this case, we consider an adversary that is passive, It is only tracking this metadata. It is not interfering with the protocol. It's not delaying packets. It's not destroying them, and so on. Right? It's participating in the network as it is supposed to, but it keeps track of all the metadata of the packets that it sees flying by. And in this case, we call this a global passive adversary because it sees everything, but remains passive. Right? And it also, in this case, it has corrupted some of the mixes, M1 and M3 specifically. But the idea is that even under these very dire circumstances, a mixnet is able to break these correspondences of packets entering the mixnet and leaving the mixnet. Right? So this is a really nice property, something that we might want to have for network anonymity. And just to sum this up, a mixnet works in the way that it has proxies. These are the mix nodes through which the messages are sent. It prepares messages of fixed size, so all of them look the same, and layers them in encryption that only a specific hop can decrypt. And then this is very specific to a mixnet. It uses fresh cryptographic key material for each packet. So you cannot link packets based on, for example, like a session key. That doesn't exist, right? Like if you send a flow into the mixnet, all of them will get their own, like each packet will get their own cryptographic key material, so that you cannot link them together to be the same flow based on the session key, for example, at an intermediate mix, right? So this is really strong, right? For each packet, fresh cryptographic key material, and it's also a fundamental difference to something like Tor. If you're thinking of Tor in terms of anonymous communication, they have something like streams, circuits, right? These things. They have a session key, which means that a hop on the way between a sender and a receiver knows which key to use in order to handle a packet. This is not the case for a mixnet, right? And then, very crucially, to break the timing dependencies, mixes will artificially delay packets. So in addition to propagation delay, because it already takes some time to send packets through a network, there comes artificial delays that will hold back packets for a specific amount of time or according to some mixing strategy at the intermediate mixes before forwarding them. Okay, this is basically how a mixnet works, roughly. And this is great for protecting individual packets, or even short flows. But we don't live in a world where we are using the internet with short flows, right? We use relatively long flows, because if you think about something that you do online, such as web browsing or downloading a file or browsing social media, you have long-ish sessions of sending many packets back and forth, right? It doesn't suffice to send, like, let's say, one email in one packet to the mixnet and your action is done. Right. So what about flows? How do mixnets fare against flows? And this question has seen some renewed relevance recently because of two major developments. So first of all, a modern implementation of the mixnet concept called NIM, in which, full disclosure, my promoter is involved, launched recently. And then, so there is a modern mixnet available that is supposed to be used for general purpose traffic. Making this question relevant, right? Like, how does it help against with flows? And then two recent scientific works have shown that deep learning methods, so the very popular methodology conquering all the fields, the deep learning methods are very effective at linking Tor connections. So Tor is another anonymous communication network. Works a little bit differently, as I alluded to before already. And these two works, Deep Coffee from 2022 and Deep Core from 2018, show that if you collect a large data set over Tor, these deep learning methods are able to pretty accurately match which ingoing connection is which outgoing connection. Right, so the question is, okay, what about mixnets? How do they fare? To quickly introduce NIM, it is a modern state-of-the-art mixnet. It's basically how you would implement a mixnet today, right? It is Rust code, it's open source, it's very nice. And it's also deployed. So if you want to know more, check out their website. The team gathered in 2018, but by now, of course, they're more advanced in what they offer, right? The aim of NIM is to propose a general purpose anonymous packet routing layer for internet packets, right? So this is quite a high aim, quite a high goal, which also indicates that you might not be able to delay packets for an hour, because that will destroy many of the relevant flows that you want to protect, right? Like, it's not useful if your web browsing session, each packet is delayed by an hour, which some older mixnet concepts might deem suitable for, let's say, email, right? Which might be okay. But for something like general purpose internet routing, you cannot assume that you can delay packets for an hour and it will work, right? So with this goal, of course, come certain design criteria that you will see in a bit. But yeah, the idea is you hook up any application to NIM, mostly any. Of course, there's limits, but should be relatively general purpose, and it will be able to provide you network anonymity. NIM itself is based on a published work from 2017 called Loopix, and thus takes over some of the key design concepts of Loopix. So NIM uses a stratified topology of 3 layers of mix nodes with n mixes in each of those layers. So a message will go through 3 hops in the mixnet and can choose a range of mixes in each layer. Clients in NIM determine this path. They choose which mix to pick for each layer. So that's called source routing because the source, determine the path. NIM and Loopix, but NIM specifically in this case, is a continuous time mixnet, which means that they don't follow a strategy where they will say, I'm waiting until I see 100 packets or until 10 seconds have elapsed, and then I will forward the batch of messages that have arrived in this time. They will treat each packet independently. So a packet comes, it has a certain delay parameter, it will be delayed for this amount of time, and then it will be forwarded on. So they work on continuous time. They're not restricted to something like batches, right? Which of course has many practical advantages because you can continuously route traffic. You're not relying on other people also sending traffic so that your mixnet can make progress. And endpoints that connect to NIM are pretty strict in how they shape their traffic. So they have a packet emission schedule that is based on a Poisson process, which means they will pick an exponentially distributed delay on average of 20 milliseconds in between sending packets, right? So there's a tick, and this tick is exponentially distributed delayed, and every time this fires, you send a packet. So you shape your traffic that goes into the mixnet. And I forgot to mention that the per mix delay that is applied to packets has an average of 50 milliseconds, also drawn from an exponential distribution. Right, so you can see that this definitely has an impact on how your traffic looks. It is definitely not the same shape as if you don't use a mixnet and you connect, for example, to a web server directly. There will be strong impacts on how your traffic is shaped. And then something that NIM and Loopix both have is, and where Loopix has its name from, is something called looping cover traffic. So in order to hide when you are actually using the mixnet for real traffic, you will continuously send messages that you will throw away when you receive them again yourself. So you send to yourself and you will throw it away. And this kind of behavior hides when you actually are using the mixnet to send real traffic. Okay, so this is NIM, roughly. And this overview, you can see that how this fits together, right? So you can see on the lower left, there's the users. On the lower bottom top left, there's the service providers that these users want to interact with. On the right-hand side, you have this stratified topology of mix nodes. So you see 3 layers, right? 1, 2, 3, and in each layer, you have 2 mixes to choose from. So if a user sends a packet towards the service provider, it might pick these 3 mixes to go through, and then it reaches the service provider eventually, and they will send it back through a different route that they picked. Crucially, there's one layer in between this. This is kind of like an edge layer called gateways in Mixnet, and they have different roles, but for our purpose, it's just important to know you will never send packets directly to the Mixnet, and the Mixnet will never send packets directly to you. You interface with like an always online gateway that is basically your mailbox, so to say, right? Like you send it packets, it will send it to the Mixnet and receive your packets also. And what I would like you to take away is that NIM is a modern representative of the Mixnet concept, and we use NIM to evaluate our attack, because this is basically our stand-in for any real-world modern implementation of this concept, right? So we take NIM and evaluate NIM in place of all Mixnets, basically. Okay, so then let's come to the question that this work answers, or tries to answer, right? Like works towards answering. Specifically, the research question: how well does a state-of-the-art Mixnet, in this case it's NIM, prevent passive gateway adversaries? So this is why I explained this position before. We're just working on this gateway layer, so in between the users and the Mixnet. So how well does a state-of-the-art Mixnet NIM prevent passive gateway adversaries from linking communicating endpoints using only this packet metadata, right? And if you are thinking about how packets are routed through the Mixnet, really only what we have left is timestamps and sizes of packets. So based on observing like continuous flows of these values, timestamps and sizes of packets, how well can an adversary sitting at the gateway position link who is communicating with whom? Right? That's the overarching question. And to a little bit foreshadow what I'm going to talk about for the rest here, the highlights are that under quite some assumptions that I will explain, so keep in mind that we of course make simplifying assumptions, our attack to link communicating endpoints is relatively fast and relatively accurate, right? So this works. We can actually, under these assumptions, say yes, these endpoints are communicating or not, right? Our adversary is assumed to only run some gateways passively, right? It doesn't interfere with the protocol, it's just tracking what it sees. We present 3 classifiers that perform this attack. We're calling them statistical, drift, and shape, and I'll talk about them a little bit later. There is this notion of the loop cover traffic, right, which you might see as a pretty strong and a pretty difficult notion to attack maybe, because it covers lots of your network activity. And we have a technique that we call flow merging that will allow us to incorporate this loop cover traffic into our attack model and thus work with it, right? It of course has an impact, as I will show later, but we can work with it in this setting. And then the output of our classifiers is you put in a group of endpoints that you would like to ask, are these communicating exclusively? And our classifiers say yes or no. That's roughly what we did here. So to visualize this a little bit, you can imagine that I replaced the Mixnet with just this block on the top, right? The adversary is running these 2 malicious gateways, and these gateways have their own set of connected users. Let's assume among them is an initiator I on the left-hand side and a responder R on the right-hand side. And you can think of this as like a client and a server, right? Like someone reaching out to a web server and the web server responding, for example, right? These 2 endpoints both have like an ingress flow direction, so anything that they send towards the Mixnet, and an egress flow direction, so anything they receive from the Mixnet, right? So this is like, just keep in mind because this will pop up later, ingress towards the Mixnet, egress from the Mixnet. And then the question we ask is, are endpoints I and R communicating exclusively with each other? And if we can say this, just from looking at the packet metadata, we kind of de-anonymize this previously anonymized connection, right? Okay, so now to the assumptions, so that we make clear what we assume before we claim our results. So the question that we are asking is, are endpoints communicating exclusively, right? So exclusively here is the key word, meaning consider a set of endpoints that you want to ask this question about. If the set is of size 1, then you're asking, is this one endpoint communicating exclusively with itself? Which means it will only send loop cover packets, right? If it is connected to a NIM, or to the Mixnet in this case, but yeah, NIM, and just idling, it will send loop cover packets. And in this case, you could ask, is this endpoint only sending packets to itself, right? If the size of the set is 2, then you're asking these 2 endpoints, are they sending loop cover traffic to themselves and also exchanging payload packets? And then you can scale this set, right? Like you can ask this for 3, for 4, and so on. But you have to kind of build it this way. Another really crucial assumption is that we assume any packets sent into the Mixnet will eventually come out and will be represented on the egress flow. So this goes back to the naming. Anything on the ingress flows will eventually be on some egress flow. There's no packet loss, right? So I'll explain later how we have 2 different setups regarding this network assumption. But for the big initial part of the work, we assume no packet loss. And that might already indicate to you also where the problem or the trouble of our classifiers lie with this assumption, right? So to make this very clear, summarize these first 2, we're only doing complete flow matching for this work, right? There's nothing where we would say, okay, there's a partial part of this group communicating that matches. We're asking, are all packets in this set of endpoints accounted for? And then we can answer this question, but there's no, this is the limit, right? And then another practically relevant assumption that we're making is that the adversary knows when the network activity of interest starts and ends. And of course, this is a little bit of an optimistic assumption because that might be difficult to determine from the outside. But for this work, we want to look at if they know, how far can they get? Okay, so now to the 3 classifiers that I mentioned that we propose. We call them statistical, drift, and shape, and I'm going to give an intuition for how they work now. So think back to the flows, ingress and egress, right? Now consider that you merge together all of the flows of the set in this respective direction. So you say initiator responder ingress, merge it. Initiator responder egress, merge this flow. So you basically turn any set of communicating endpoints, their flows, into two, ingress and egress, by just merging these flows, right? This way, you will take care of Loopcover traffic that goes out through a different route than the payload traffic, right? Now, if you compute the time difference between the egress packets and the ingress packets, that kind of gives you the delay of the packets through the Mixnet. And because these parameters are public, we know what we expect this delay to be from the Mixnet, right? So because, of course, this is a published system, we know the parameters that they choose by default. So we have an expectation. And now we can compute for any tested pair the likelihood that the computed delay is consistent with this expectation. And this is then our score. And if the score is above a certain threshold, we say, OK, this is a matched flow pair. Or if it's below, we say it's an unmatched one. And behind this is the intuition that for matched flow pairs, their delay will follow a stationary distribution. But for unmatched flow pairs, it will drift away. Right? Like the longer you watch, the more it will drift away from the stationary distribution. So you can use this to discriminate. Right? So this is in quotes, just because it's like, you really only compute these values, right? Like it's a statistical classifier. We also follow a similar, this concept of drift in a deep learning-based classifier. So this is the first of our two deep learning-based classifiers, drift, because it exploits the same idea, right? The same notion that for matched flow pairs, their delay distribution is stationary. For unmatched one, it drifts apart. But instead of modeling this explicitly, in the case of the statistical classifier, we learn this underlying distribution from like a large data set that we collect, right? So we train a convolutional neural network to learn this directly from the data. This has the potential to be a bit more general than a statistical classifier, but we'll see how they pair up later on in the results. And then we have the third classifier, which is also a deep learning-based one. However, it deviates conceptually from the previous two. It actually follows in the footsteps of related work, in this case, Deep Coffee, which is the strongest flow correlator for Tor. It adopts a very, very similar network architecture. And the idea is that instead of exploiting the drift between flow pairs, it will transform flow pairs into a lower dimensional space that is optimized for a distance metric. And in this distance metric, matched flows are grouped closely together, and unmatched flow pairs are are spaced far apart. Right? So you compute this distance metric, and based on that, you know whether the flow pair is matched or not. I mentioned it's adapted from Deep Coffee, and this learning this architecture is called triplet network architecture. Okay, sorry, I hope you can read this. The good thing of this is that once you've transformed the flow pairs into a lower dimensional space, this is called the embeddings. Computing this distance metric is pretty cheap, so you can do this comparison fast. Okay, so these are our three classifiers. The first two ones exploiting drift, the last one not. And the last two ones are based on deep learning methods. The first one is a statistical one. Okay. I mentioned before we collect data to evaluate our classifiers. So let's talk about this data collection setup. In total, it's 6 data sets that we provide and evaluate. Each data set has 35,000 flow pairs, and each flow pair is a download of a file of size 1 megabytes. This is our exemplary use case. So an endpoint reaches out to a server that supplies this endpoint with a 1 megabyte sized file, and we trace the metadata for this download 35,000 times for each data set, right? We do this in 2 setups, and they model roughly what I mentioned before, that one of them does not assume, is unrealistic in terms of its network conditions, and the other one is more realistic. So in one of them, there will be no propagation delay and no loss, no packet loss, and the other one is more realistic, more real-world network scenario, right? Specifically, the isolated one is the one where we control everything, like we set up a minimal NIM network using Docker containers on a single host. But this means that there is no realistic network in between those containers, right? So that means no propagation delay, no loss. You can see how we do this like at an abstract layer here, level here. This is the isolated setup. We as the adversary are sitting as the gateway position in between an initiator and a responder. And the initiator asks, using curl from a Python 3 HTTP server, for this 1 megabyte-sized document that it will download, right? And we track the metadata for this. The idea of this isolated setup is that we want to see at its core, what does the Mixnet contribute to anonymity, right? So if you leave out any kind of additional impacts and effects that the network will add on top, because of course delay has an impact, because packet loss has an impact. If you take this all away and you focus on the Mixnet, what does it contribute to this? So that's why this is the first setup. The second one makes more realistic assumptions in the sense that it is the live network, the live deployed NIM Mixnet that we hook up to with our infrastructure to collect data. So that means there will be mixes and so on provided by the community, run in the real internet. So there's realistic network effects, right? Here, of course, it's critical to do this in an ethical way to avoid collecting data from unrelated users. But yeah, we describe in the paper how we achieve this. And the goal with this setup is to model more the real world setting. Yeah, so the 6 datasets that I mentioned, 5 of them we collect on the isolated setup, 1 on the live network setup. To run quickly through them, there's the first dataset, which is called baseline, which will just evaluate default NIM. If we don't change anything relevant for message transmission, we have to make a couple of tweaks for data collection, but nothing relevant here. If we just use default NIM, what is the data that we can gather when we run this? Second one is no cover, where we disable any kind of loop cover packets. And of course, the idea is that we can see what's the impact of adding this, right, in terms of protection against analysis. I mentioned before this parameter of how long a message is delayed at each of the mixes between sender and receiver, right? And for low delay and high delay, we change this parameter from the default average 50 milliseconds down to 20 or up to 200 to see. Of course, you can think of this like there's more packets that this packet can mix with if you increase the delay. There's fewer packets that the packet can mix with if you decrease the delay, right? So what is the impact in terms of anonymity for this? And then I'm not going to go into any detail for the last one, but just for completeness, the last one is called 2-to-1. And on the live network setup, we collect one more data set called live NIM, which is basically baseline, so default NIM, but now on the real deployed network. Okay, so with this out of the way, let's actually look at some results. These are our result plots. Our result plots are receiver operating characteristic curves, so ROC curves, if you have heard this term before. That just means the true positive rate of the classifier against the false positive rate of the classifier at various points along that way, right? So if you think about it, an ideal classifier would be located in the top left corner of this plot, because it would have a true positive rate of 1.0 at the lowest possible false positive rate, right? It makes no mistakes. That's the perfect classifier. Of course, that's the goal. You can see we don't end up there always, but yeah, that's where the best one would lie. And if our lines were below this green line, we would actually be doing something wrong, because the green line is just a random classifier, right? If you're worse than the random classifier, something is wrong with your system. So we want to be kind of between this space, right? In this plot, you can see 2 colored lines, the blue one and the orange one, that are related to our classifiers. There's one missing, the shape one. And that's the reason is that we evaluated the shape one, of course, also, but it performed really badly compared to the drift and the statistical one. So for the next couple of plots, we leave them out, but we'll return to the shape one in a little bit, okay? So for now, we focus on the deep learning-based drift classifier and the statistical classifier, which essentially exploit the same information, right? The delay distribution. And we can see here that if we increase the data that we feed to these 2 classifiers, they, of course, increasingly become better. But already at only processing 100 observations and packets is not exactly 1-to-1, because one observation is its payload packet and its associated acknowledgement packet. Keep this in mind, but roughly equal, right? 100 network observations. We already obtain a true positive value of 0.6 for the drift classifier and 0.47 for the statistical at a false positive rate of 10 to the power of -2, which is really good in the sense that it is not much data and significantly better than the random classifier. And you see that the more data you feed, the better it gets. Until like this symbolizes all packets or all observations in a flow, you essentially have a perfect classifier, right? Pegged at the 1.0 TPR level. Yeah, I should have mentioned this is dataset baseline, right? So default NIM in the isolated setup, no propagation delay, no packet loss. So of course strong constraints, but in the setting, our classifiers are fast and accurate. Now the question is, does this loop cover traffic add anything? Like, does it help make our attack harder? So this is where we contrast the baseline data set as before and the no cover, so where we removed all loop cover traffic, these two data sets. And the line for the number of observations that are represented here is 100. So the lowest number of observations that I showed before, this is where we compare performance at, okay? And you can see, yes, it has an impact. Like loop cover traffic is really helpful in thwarting our flow matching attack, in the sense that the performance, the true positive performance, our classifiers reach at the in the baseline data set at 10 to the power of -2 is obtained 4 orders of magnitude lower at 10 to the power of -6, so much faster, right? Or at a much better performance point, right? If you remove loop cover traffic, so it's very helpful. What if you change the packet delay parameter at the mixes, right? If you make it higher or lower, what changes? So we compare the baseline data set with low delay and high delay. And you can see that the expected impact materializes. If you reduce the delay, our classifiers obtain better performance. If you increase the delay, their performance goes down. But actually, like a relatively significant amount, right? Like if you look at again at the false positive rate point 10 to the power of -2, for the low delay data set, it's essentially again perfect classification, while for the high delay one it drops to 0.15, maybe, roughly, right? So there's quite some significant gains or losses to be had if you change this parameter, yeah, quite a bit, right? Like you reduce it from 50 to 20, or you increase it from 50 to 200 per mix. And then now let's look at realistic network effects, right? Because so far this was the isolated setup. So now we compare the isolated setup baseline data set with the live NIM, live network setup, which means it's default NIM in either case, but in the different network settings, right? And we have introduced the shape classifier here again to show how it performs, how badly it performs in comparison to the others. But also in these two different, to show how it performs in the two different setups. So first of all, you can see that the violet line is always lagging behind the respective other blue and orange lines. But then the second more important takeaway from this plot is that in the live NIM dataset, we see that our classifiers really struggle. The performance goes down quite a bit, quite significantly, which we attribute, of course, only to like the network effects, because that's the thing that we changed in between these two datasets. Okay, this is the amount of results that I want to show. There's more plots in the paper if you want to see more plots. Let's talk about countermeasure ideas, right? Because we have shown, okay, under these conditions, flow matching is doable with the classifiers that we presented. What can we do against this? And in maybe the most important, like I've been starting with the most important ones, there's a couple of others, but the most important one should really try to invalidate this assumption that any packet going in comes out in a set of endpoints that is communicating exclusively. You kind of have to break this assumption, because that's, for example, what the live network dataset showed, that if you have packet losses and so on, we start to have problems, right? So maybe there's a way to introduce new cover traffic that leaves these merged flows ingress to egress. For example, you can think about like packets that are dropped along the mix path, right? Like you say, okay, mix 2, drop this packet, right? So it goes in, it's on ingress, but it's not on egress. Or you can find a way for how you involve other endpoints. These could be users, but more realistically, they would probably be service operators that you just exchange random packets with, basically, right? You send them something, so it's again on egress, but not on ingress, but not on egress. Or they send you something, so it's not on ingress, but on egress. And the crucial point here is that it needs to be outside the set that the adversary is observing, right? If it goes somewhere else, then the adversary has no way to include this additional endpoint in the set that the adversary is evaluating. More ideas is that at the moment, payloads and acknowledgement packets, they have different sizes, so it can be easily discriminated just based on the size of the packet that you see flying by, which helps us, which helps the classifier. It adds to its performance. So if you make them equal sized, you take away this this level of discrimination between these packets, right? Of course, that's a big trade-off because you have to think about, do you make the acknowledgements the same size as the payloads, which that's a tough operational decision to make. But yeah, this would help for sure, right? The per mix delay of the packets, you can change this. We showed this. It has an impact. Like it helps prevent, like not prevent, but like make our attack more difficult. So you can increase it, or maybe also there's a way to make them variable, like to introduce classes of delays that applications or users can pick from for their traffic. This is also related work of Ines, in case you want to look into this. And finally, if you increase the size that each packet had, so more data was sent in one packet, you would reduce the number of observations, which, as we showed, of course, leads to, like, if you have more observations, you're better performing in the attack, right? So another countermeasure is to increase the packet size. These as countermeasure ideas. Let's go to takeaways. We saw that mixnets are indeed a very powerful and also a very versatile tool to achieve network-level privacy. You can mold them into very many different use cases, optimize from them, right? So they're quite relevant and very powerful. However, they're primarily good for single packet or short flows, right? Single packet flows or short flows. Not so much for modern long flows, right? We have many packets going back and forth and so on. We show this in our work in the form of 3 classifiers that exploit this fact, right? That there will be realistically long flows going across these networks, and they perform flow matching, which is a specific type of attack that I explained. With the assumptions that we make, our attack is fast and accurate, and shows that even a very modern state-of-the-art implementation such as NIM is not immune to this de-anonymizing threat and has to think about how this affects them or how this impacts them. And finally, there is like an indication of where to go with a potential countermeasure, which is exactly to break this assumption, this endpoints closed set condition that the set of endpoints that is communicating exclusively and all packets are accounted for, right? If you can try to work with a countermeasure in this direction, that indicates that this might help drive down the threat of flow matching. That's the takeaways, the papers that I mentioned in this talk, and I'm happy to take questions. Thank you.